Welcome to this video about understanding engine braking. Here I am going to explain the purpose of braking in an engine, several methods of running in an engine, and the reasons behind each method. And for this video, I'm going to be using the terms braking and running interchangeably. So getting right into things, what is engine running? Well, very simply put, and I'll explain in more detail later, when parts are newly manufactured, they're not quite the appropriate finish when it comes to optimum engine running. What do I mean by this? To understand this, let's look at two aspects of an engine that makes what we'd call a good engine. What a good engine is simply an engine that has A, good power for its size that is, and B, low fuel consumption. Now interestingly, both these points are related to the exact same aspect of the engine, and that is the way the piston ring contacts the cylinder wall. I'm going to say that again. The way the piston ring contacts the cylinder wall. Why is this, you might ask? Let's have a look. Now most of us understand the basics of how a piston internal combustion engine works. Fuel-air mixture is ignited, either by compression ignition or spark ignition, and the rapidly expanding gases force the piston downwards, which turns the crankshaft and gives you lots of useful movement. Now there are many ways to get more power if we so desire, but for this video I'm only going to focus on two of them, and the first is more fuel and air, and the second, more efficient combustion. So obviously if you want more power, one way to get it is to burn more fuel, because more fuel means more energy. The obvious downside to this, however, is that fuel costs money. So more power in this case means more money. So focusing on the second option, more efficient combustion. Another way we could get more power is to increase the efficiency of the engine in terms of turning fuel into movement. There are many ways to do this, however, the one we're going to focus on here is related to these things, your piston rings. Why? Think of how an engine works. Here's the famous autocycle diagram that we've all seen, and here you can see the intake stroke where the fuel-air mixture, or in the case of a diesel, just air, is being sucked in. Then the compression stroke, where it is compressed, and then we get to the power stroke, which makes all the wonderful noise we like to make so much as kids. If we pause here and think about it, this stroke is singularly responsible for basically the entire purpose of the engine, transferring released energy into movement. And the way it does that is by harnessing the expanding gases and turning the crankshaft with them. Now, one reason I don't like animations is that they make the world seem like a perfect and orderly place when it is anything but that. This diagram might give you the impression that everything is perfectly regimented and timed and extracted, etc., so there's no room for improvement, and the world would be a perfect happy nirvana of exploding dinosaurs. But in reality, however, engines leak, and I don't just mean British engines, I mean all engines. And I don't mean externally, I mean internally as well. You see, in the perfect world, all of the expanding dinosaurs are captured by the rings, and all the power is transferred to the crankshaft. In the real world, however, the rings leak, and some of the gases escape past. Why this is a very complex matter involving cylinder surfaces and ring surfaces and a whole bunch of physics I won't get into here, but fortunately, most people can understand the basic principle of why this is. So think about the objective. We want to not allow combustion gases by the rings, so we can harness all the power possible. What is the best way to not let something leak? A perfect seal. What is the best way to seal an engine up? Taking a complex concept and simplifying it, it is to take two mating surfaces and create as much contact between the two so that whatever it is you're sealing against doesn't leak by. A common way to seal things up is to use a gasket sandwiched between the two mating surfaces, and why this works is because the gasket conforms or squishes into all the little micro imperfections of the mating surfaces and prevents stuff from leaking by. Another way to seal, that you may not be aware of however, is to make the mating surfaces as flat as possible, and not just flat as in, it looks flat to me, I mean flat as in mirror finish flat, microscopically flat. Same principle applies here actually. The flat surfaces will make a lot of contact between each other so that the molecules cannot squeeze by. The reason that two metal surfaces don't bond together naturally, of course, is because metal is a lot more rigid than a gasket. If the two surfaces were pliable, they could be squished together and a seal would form there, but since metal is not so pliable, you need to have the gasket, or in this case, machine them microscopically flat, as we just explained. Now normally what you'd expect is that if you put two pieces of metal together, even very close fitting metal, that liquid would still leak out. But if you take two completely flat pieces of whatever material, you might be surprised to find that it is in fact possible to seal even against liquids and gases without a gasket or seal. Now I apologize if this sounds a bit winded, but here is now where all is going to start coming together. Now that we know that two pieces of metal, albeit very flat pieces of metal, can be used to seal two surfaces together, we now can start to see how this applies to the combustion chamber, namely with the piston rings and the cylinder, which both happen to be made out of metal. If we have the moving surface, in this case the piston, and the stationary surface, in this case the cylinder wall, very close to each other and finished to that microscopically flat surface we were just talking about, then we can create a good seal against the expanding gases and transfer more of the power to the crankshaft instead of having it just leak by. Sounds good, right? Unfortunately, there's a problem. Expansion. Parts expand and contract with heat, and that expansion and contraction causes differing amounts of clearance, which is exactly what we don't want. Now you might think, so what? How much clearance can there be? And the answer is not much, but it doesn't take much to render the entire thing useless. So what we need to do is close the gap up, obviously. But the problem is that if we did so, the piston itself would seize in the cylinder because of the temperature variations of hot and cold. So the clearance must be left in there to account for this. The solution is one you've probably heard of before, and that is called the piston ring, or rings in most engines. Piston rings are the compensation because they can expand and contract while maintaining a seal against the cylinder wall surface because there is a gap at the end of the ring, which opens and closes up depending on how warm or cold the engine is. Okay, great, you might say. But when are we going to get into the part of actually running it in, and what does all this have to do with anything? And that's what we're going to talk about now. So, we now know the goal of what we want to achieve. Less internal leakage, which is technically called blow-by. We also know that the parts that are involved and what their purposes are. Piston rings to expand and contract with heating and cooling, piston for lateral support and to hold the rings when combustion gases push it downward. Also, the piston serves to form as a shape of a combustion chamber. That's why you see all these different shapes of piston heads between engines, but we won't get into that here. And the cylinder wall for the rings to seal against. Now, reality kicks in. We know we want a perfectly flat sealing surface between the face of the ring and the cylinder wall, right? Because if we didn't, it wouldn't work. But the question is now, how do we get two perfectly flat pieces of metal between each other? Number one, you could make one part flat and another part flat and then put them together. Very simple, right? And two, you could take two parts and then polish them against each other so they wear into each other. Now the first might seem like a reasonable method, seems how we have factories with all kinds of technology to make these things, right? However, when you start to delve into things, you quickly realize just how difficult it is to make something perfectly flat and to a specific size. Here is some footage about polishing a crankshaft journal, which you can see here is very shiny. It takes quite a long time to get a satisfactory result, so obviously the first option is going to be right out, especially for mass production vehicles. So that leaves us with the second method, rubbing the two surfaces together and wearing them into each other. And that, my friends, is what we call the break-in process. Sigh of relief. The run-in or break-in is that rubbing of these two parts together to create the smooth sealing surfaces between the two so that they seal against losing precious combustion gases. And that's the whole point of running or braking. Now we're going to explore the various ways people run in their engines and also why. Now you may have heard of various braking methods, and while each of them has their own specific applications, the common theme I've heard from most people telling me their braking method is that they don't know what they're doing except for the explanation told to them by the mechanic or machinist, or in this day and age, to internet. They don't understand the process and the real reasoning behind what it is they are doing, and that's what I hope to help you understand with this section of the video. Okay, so the first method. Your method might vary slightly, but the basic idea is roughly the same. Do not exceed a certain RPM or speed or amount of throttle for the first X amount of time. Then after X amount of time, do not exceed a slightly higher RPM, speed or amount of throttle. Then when you reach X amount of time or miles, your engine is now classified as run-in or broken in, and then you can use it however you please. So this is essentially how I learned to break in an engine, and I'll be the first to say that I religiously followed this method for years and years. After all, what was good enough for Toyota, and that car lasted 35 years before needing an overhaul, was good enough for me. And I never had any problem with any of my engines, either with power, fuel economy, or oil consumption, except my two-strokes and rotary engines, obviously. Now the logic behind this method is the following. Since newly manufactured parts are not smooth, namely the piston rings and cylinder wall, there is an extra amount of friction that is taking place, which normally isn't there in an already running engine. This extra amount of friction causes extra stress and, more importantly, extra heat. So the reason you're keeping off heavy throttle and not exceeding a certain RPM is to keep the heat out of the rings so they either don't seize or break. Once you wear past the roughness on both sides, the friction is then greatly decreased, and now you can run your engine to its full potential. So that's the first method. However, there's another method that's been floating around these days, and the method is as follows. First, after warming up and checking your engine out, you take it through a series of long, half or two-third throttle pulls and then let the engine do the braking, meaning you don't use the brake pedal, you just let the engine spin down, a bit like this. Then for the second pull you do another series of pulls with slightly higher throttle. Then finally you go for 4 throttle pulls. Then you head home, change your oil, and then you're done. Go racing. Now I'll be the first to say, this method made me cringe when I first heard it, since it seemed to go against everything Lord Toyota had said. However, here's the basic rundown of the logic behind it and why it's supposed to work. The basic theory behind this is that rings need a decent amount of throttle and pressure to properly seat. Think of it like sanding paper. If you just glide the sanding paper very lightly over a certain surface, you're not going to have much of an effect. But if you push down on the sanding paper with more force, then you are going to get the friction that you so desire. So, when the friction is greatest, This is when you want to take advantage of wearing in the rings as firmly, although it's not quite the right word, as possible, and make sure you get a good wear in. However, since friction is increased, you want to do this in short bursts and allow the engine to cool for long periods of time afterwards, hence the brake periods. Once this hard braking method is used, then there should be enough wear done so that you can use your vehicle to its full potential, which could be quite useful for people like racers or people who are impatient like myself. So both methods have their reasons, both have their advocates, but which one is the one true pathway? Answer? Both. You see, the reason I was taught by my father, who grew up in the early 50s, to use the soft braking method is because the vehicle he bought was a late 60s Toyota, and during this time the method for finishing cylinders was a lot more crude and specifications were, simply put, much less stringent, since the skill and knowledge of the workforce was considerably lower during the time, not to mention the quality of tools a lot less as well. This means that the finish of a cylinder was not necessarily bad, but it was less consistent. This is why the safe approach to braking was usually dictated. However, as technology increased in precision, materials advanced in consistency, and manufacturing efficiency increased along with it, parts could not only be made with greater speed, but also with a tighter degree of consistency, meaning that now an engine's cylinders can be created with a very narrow margin of variation in the roughness of the cylinder. Not only can the machines create these surfaces, but machines can accurately verify these easily as well, and it is because of this that engines can be broken in a remarkably short period of time compared to before, sometimes in as little as 60 miles. Now, to an old school mechanic like myself, or old school trained, this seems a bit unreasonable and strange, but if you took time to explore and understand the technology, you would then realize why the rough braking method can indeed work without the use of a dynamometer and a vast array of gauges to monitor things like exhaust gas or cylinder head temperatures, because the newly rebuilt engine is finished almost to a level of an already broken-in engine, and therefore much less heat buildup and stress will occur during the hard run-in, and also much less time is needed to wear in the appropriate surface. So what does this mean for you then? Well, in simple terms it means the following. If you buy a new car or motorcycle, and assuming it's not a budget motorcycle like this, like basically every machine I rebuild on this channel, then you can utilize the rough braking method, because the machinery used to finish the cylinder in your vehicle is very precise and consistent, oftentimes automated. But the big question is, does it work? I can tell you from first-hand experience that yes, it does work. You see, I gave this a try on my own scooter about 15 years ago, and also a shiny new DC-5 Integra at the time. I essentially followed a hard braking procedure, and then changed the oil and didn't think about it again. Actually, that's not true. A large part of me wondered if I had done an incredibly stupid thing and would regret it later on. But 15 years later, that Integra is still going, albeit it only has 100,000 miles or so on it. I'm not sure what happened to the scooter, but I did use it for about a year and never had any issues with blow-by or oil consumption, so I assume it worked. But also, if you take a look at how factories frequently test their engines, it's clear that they're unafraid of destroying or damaging them, as well as running them up to peak power right out of the box. So already we can see the hard braking method does in fact work, and it seems to be now what every factory, race team and engine builder does regardless. But then that begs the question, does the soft braking method still have any merit, and does it still work? And the answer to this is yes, it does, and here is why. While it's true that most big-name manufacturers, and now even many independent shops, are capable of producing very high-quality, consistent finishes on cylinders, the equipment needed to do so is still quite expensive. So, at least for now, there are many thousands of shops that still use the old way of finishing cylinders, which consists of a rigid stone-honed system like this, and manually operated honing machine, or in small cases a drill press. Now, inexperienced machinists can still produce a very high quality finish with just their hands, so to speak, but being able to tell how skilled a machinist is going to be largely unknown unless you're willing to shell out the money for a profilometer, which is this thing, and they're usually about £1,000 or more. So in the case of having your engine machined at a machine shop where you're unsure of the methods they're using to finish the cylinders, or in the case of very simple machines like cheap motorcycle engines or petrol streamers, where a simple that'll do finish is the most cost-effective way of doing something, then the soft braking method should be used at all times, as you won't know if your engine will overcook itself at high loads, until it lets go obviously, or in this case, seize up, and yes, I have done that before. So basically, because it's more cost-effective to do things the old way, there's still people who do things the old way, to keep costs down obviously, but that means you should still follow the old way of breaking it in, which is slow and steady wins the race, so to speak. So, in review, new vehicle or professionally rebuilt motor where the honing methods are state-of-the-art technology, you're safe to use the hard braking method. And it seems like that's what every manufacturer is doing these days. I can't emphasize this enough, because people like me who are stubborn and cling to the old ways will fight tooth and nail to say, no, you're doing it all wrong and the world's going to explode if you do it that way. But if you have your cylinder or cylinders machined out using a more cost-effective or handmade solution, so to speak, I recommend the soft method of braking. Now, of course, each engine is going to vary in terms of hour usage or miles, in terms of the braking that is, so refer to the specific braking procedures relating to your vehicle, or if you can't find them, look to a similar vehicle and then copy those braking numbers. But a quick note, however, before we go, the only thing I like to do as a little extra on top of people's instructions is if you have a small oil capacity engine, like a Honda Super Cub for example, is to change the oil after the first 20 minutes of warm-up and riding. The reason is because the roughest particles are going to be worn off in these first 20 minutes, 15 or 20 minutes obviously, it doesn't have to be exactly 20, and these particles will be running and be suspended in your oil. Now, while I doubt that has a big effect, it always has given me peace of mind to watch all the glitter and metal drained out immediately. And believe me, you'll be surprised at just how much actually comes out, not to mention how washed out and dark your oil becomes in just a few minutes. But if you have a larger oil capacity vehicle, rest assured it seems to be fine to leave the oil in there until your first recommended oil change. Millions, literally millions of people have done it, and millions of people still have reliable long-lasting vehicles, so it's likely not that big of a deal, and I'm just overthinking things as usual. Now, I'll have another video on the specific break-in methods and how to execute them, but here I'm going to end this video for time's sake. I hope this video was helpful at helping you understand how the break-in works and why we are doing it and why the reasoning is between certain methods. I'm Meaning Motorman, so until next time, goodbye.